For the next talk, I would change my roles a little bit. Up until now, you have heard me as a moderator, but I would be presenting now as well, with Ricardo as well, my friend. So the first question, again, I like provocative questions, so I would start with a provocative question once again. How many of you have heard about Industry 4.0? Oh, there are still some hands that are not going up. Both hands going up, great. Jean-Michel is sitting there, so he hasn't heard about Industry 4.0. What is Industry 4.0 about, actually? I mean, the buzzword, everyone knows the buzzword, right? It's a buzzword, Industrial Internet of Things, Internet of Things. It's nice, it sounds cool, it sounds hip. But what the hell is it about? So, Industry 4.0 is about connected machines. So, Industry 4.0, where does the 4.0 come from? Can anyone just answer me this? Where is the 4.0 coming from? Just a show of hands. I just have some time, so please. Yes.
It's a fourth revolution.
Fourth industrial revolution, exactly. We have had 3 successful industrial revolutions up until now. So all of these things, PLCs, conveyor belts, robots, working automation. And now we have the 4th industrial revolution, where machines are talking to machines. And that is what we see on this slide. So this, on the left, is your traditional automation pyramid with your traditional layers. Right on top sits the ERP, Enterprise Resource Planning. Then you have MES systems, manufacturing execution systems. Then you have SCADA systems, HMIs. Then you have the PLC control level that is controlling the devices. And on the absolute bottom is the real machines, the robots, the vision systems, the sensors, all kinds of nice and fancy things that you use to automate things in industrial automation. But where are we headed? We are headed on the right side, where there's not really a strict hierarchy, but things are talking to other things. That's why we say Industrial Internet of Things. So a machine, theoretically, a machine can be anything. In this case, a robot can talk to a machine vision system to solve a robot vision problem. For example, robot vision is a really nice and fancy use case. A robot can talk to a woodworking machine. A vision system can talk to a CNC machine, who knows? So all these machines are talking to each other. And that is where we are headed. And that's why we need a universal language that the machines use to talk to each other. And exactly this universal language is known as OPC UA. And OPC UA brings us reconfigurability, IT security out of the box. So OPC UA is a standard which out of the box provides you security, reconfigurability, but is that enough? So the plain answer is no. If the language is OPC UA is fine, it's good. I'm speaking in English, but if you don't know how English works with respect to semantics, then you would not get whatever the hell I'm speaking. So the semantics for different domains are being defined by the domain-specific experts. In this case, our domain happens to be machine vision. So OPC UA for machine vision is the domain-specific OPC UA standard, which solves or looks at machine vision systems as a whole. Not really which camera, which image sensor, which frame grabber, but from a system perspective, machine vision systems perspective. VDMA hosts this standard, and on your screen right now, you see all the players that have built up this standard from ground up. We take OPC UA as the basis, but we define machine vision expertise on top of that, the so-called OPC UA for machine vision companion specification. Next up, we have some introduction to you. We define the standards in parts. The first part of the standard was already released in 2019. And the aim of the OPC UA for machine vision standard remains the same for all different parts, which is easy integration and to provide standardized behavior and interfaces. So the fundamental concepts in the part 1 of the specification is control, which we achieve with state machines. The second is recipe management, because application-specific things you can't really standardize. That's a no-brainer. I don't really have to explain much on that. So that's why we define something called recipes, and we provide the ways to manage these recipes, which in turn solves the problem. Then we have result management. And in the end, we have configuration management. Mind you, all of these things that I have mentioned, results, configurations, and recipes, these are all black boxes in part one. So we don't have standardized recipes because you cannot. Depends on the application, what recipes you use. But what we provide is the management of these things. So you load recipes, you start playing with the state machines, and you monitor the system. So my colleague Ricardo and I, we happen to have written the part 2 of the specification together, and he happens to have implemented the part 1 specification on a MVTec product as well. So I would now hand over to him. He is also a real expert on OPC UA and machine vision itself. So welcome, Ricardo. Let's have a few words. Yeah, this is forward. And if you want to show something, then.
OK. Hello, everybody. My name is Ricardo. I work at MVTec. I'm a software engineer. And I am the OPC UA expert for my company. I was the one to help push the implementation of OPC UA inside of our products and use of the concepts that were defined on the standard, not only as part of OPC UA, but as an integral part of our product. So the product that this is implemented on is called Merlik. And Merlik is an easy-to-use, all-in-one, fast setup, flexible solution for OPC UA and machine vision systems. This means that, for example, we provide you interfaces for connecting to your cameras using GigaVision standards, as our other colleagues have demonstrated, using GigaVision, USB TriVision, Genicam TL, QExpress. And we also provide an integration solution where you can connect via OPC UA or some other real-time protocol using a Hilser card. Inside Merlik application, you can create your own vision application by using our tools, which include all the algorithms that you will need for making applications. So inside these concepts, as I mentioned, OPC UA for machine vision system not only defines what a machine vision system is, and also defines several core concepts. And one of these core concepts is the control, and this is done via state machines. We assume that a vision system is always executed as a sequence of steps. And for this, we define 2 state machines. The first state machine is called a vision state machine and controls 4 core steps, which is the pre-operational state, the halted state, the error state, and the operational state. In the preparational state, as its name suggested, is where we do the setup of the application, where we initialize all of our interfaces and our software. The error state is, as the name suggested, where you find errors, and the halted state is where, for example, when you are going to turn off your application, where you go for releasing all of the application. The operational state, in this case, is just a parent state to another state machine, which is called the automatic mode state machine that includes 4 substates. In these 4 substates, you have the possibility to do different things. So when you go to the operational stage, you usually start in the initialized state. And in this initialized state, it's where you have the system is ready, waiting, but there's no selected task to execute. Then when you select a task that you want to execute, you then go to the ready state. And then you can, when you decide to execute this task, you can there go execute the task as in a continuous mode or in a single mode. So that means that single mode is just execute once. Continuous mode is continue executing until I tell you to stop. The next core concept of the OPC UA for machine vision system is the recipe management. And in the recipe management, we have to first define what is a recipe. A recipe is a single machine vision task. So reading a barcode, reading text, analyzing a piece, that's a single vision task. As my colleague mentioned, for us, for a standard perspective, everything is a black box. We do not tell you, for example, how this should be implemented on your side. You are free to use any algorithm that you want. We do not care about the specific details. We only care, for example, that a recipe exists, and a recipe has a unique ID that you can use to reference the recipe. And you can also have, for example, in a system, multiple recipes. It's not limited to having only one. You can change between the recipes before you execute them to execute different vision tasks. And you can obviously execute it, as I mentioned, between continuous or single jobs. In Merlik, for example, And we implemented, for us, recipes are VisionSTR, which is just a binary file that we use for executing, and an additional parameterization file that we use to contain parameterization and metadata information about the recipes. So what are the inputs and what are the outputs? That's what we consist of our recipe. In your case, it could be anything that you want. When you provide recipe management in the machine vision system, you need to provide an object. And in this object is called recipe management, and it has 3 mandatory things that you need to implement, which is one method that you allow you to prepare a recipe, another method to unprepare the recipe, and another method to get all the available recipes that are in the system so that you can know what is available. Additionally, you have a lot more other things that you can implement that allows you to have, for example, different types of application. If you want to upload a recipe into a system, if you want to remove a recipe from the system, if you want to, for example, leave a specific recipe to a particular product, you can do that. All of this is optional, but the only mandatory things is prepare, unprepare, and get a recipe list. The next concept is configuration management. Same as recipes, configurations. Well, in configurations are everything that guarantees that the result is always the same. It's a very strange thing to say, but basically what it means is, for example, even in identical systems, you will have slight things that are not exactly the same. So you might want to, for example, configure your GPU in a specific way, or configure your camera in a specific way because of the environment that it's in. And that thing is a configuration for us. So configuration just guarantees that we have the same results between different systems. Configuration also has a unique ID. That means that it can be referenced only as a unique ID, and what is inside we don't care about. It's also a black box. Machine vision systems can have multiple configurations. However, unlike recipes, only a single configuration can be active at any given time. You cannot have a GPU configured in 2 different ways, right? So in our case, in our parallel Mirror Lake, changing configurations with Mirror Lake from the outside is unfortunately not available. However, we do provide tools to change the configuration, but it is not via OPC UA. You have to use our internal software so that you can use this. So in this case, for example, for our implementation where you see our OPC UA server, you will not find a configuration management object. You will only find it will just not be there because we do not allow this thing. And this is something that the standard allows you. So if you have certain things in your system that is not defined on the standard but is not available in your system, you might not want to implement this, and this is also allowed. So in configuration management, there's 4 things that are mandatory. Is, again, get a list of all the available configurations, get information about a particular configuration, activate the configuration, and which configuration is activated. And additionally, we have also optional things that you can also implement, like, for example, transferring a recipe, getting more information about configurations, removing a configuration from the system, etc. The next concept is result management, and this is where things get a little bit more interesting for a lot of people. So there's different types of results. Machine vision system can have multiple types of results. It's not that we have only numbers or we have only booleans. So usually results are composed of 2 types of things. One is simple data, transferable data, and metadata. Simple data is just simple statements, for example, numbers or booleans, for example, where a piece is okay, not okay, it's just a boolean, and this is simple data. We also have transferable data, for example, images that you can transfer from one system to another if you so desire. This usually takes a lot more time and usually requires that you request the data from the system. And the metadata. So one of the most important things that we wanted to include with OPC from machine vision is the inclusion of metadata. So we are not only caring about you, for example, giving you a Boolean, whether it's okay or not okay. We also want to give you the information of how that Boolean was generated. What recipe was it doing? What job was it executed on? At what time was it created, this result, etc. Because all of this information allows you, all this rich information allows you to create different types of application, very rich applications. And results are using obviously for controlling production or for just analytics on the ERP side. There's different ways of delivering results into the system. The mandatory one, the one that you should always find available, is the use of result-ready event. That is an OPC UA event. This is a fire or forget thing that you can send into your server, and to from your server to your clients, and includes all the result information. It includes all the metadata, whether it includes the configuration used, the state, the job ID, etc. And additionally, if you have only simple data, you can also include it inside the event as part of the result content. We additionally have another way of getting results, which is as I mentioned, there are multiple ways. We can use events. We can use query methods, which is just calling a method, say, give me result 1, 2, 3, or 4. We can use variables inside a folder. If you want to just read a variable, that's also possible. Or we can use file transfer when we have complex data to transfer. And for that, we have this other object that's called result management that I mentioned. It has 3 mandatory things. Get a list of results based on some filtering criteria, get some result by ID, or get their components of the result also by ID. And additionally, we have all of these optional things that you can also use, which is the variables, the result transfer, and so on. There are however, when you implement a OPC UA for machine vision, you have to have some application considerations when you implement it. The thing is, for example, that IDs, when I'm talking about an ID, it needs to be a unique, system-wide unique ID. That means that no objects in the system are allowed to have no objects of the same time are allowed to have the same ID. That means that, for example, cannot exist 2 recipes that have the ID number 1 or number 2. That's why we have, for example, 2 types of ID, the internal and the external ID. The internal ID is usually defined by the system and is used to keep track of the information. The external IDs are usually defined by the customers and used to serve a particular purpose in the application. So, for example, if you have a recipe, if you internally might assign it the ID number 2, but this doesn't tell you anything to your customer. So they might want to add an additional ID, an external ID that says, for example, this recipe is used for product 32, right? And this is your external ID, and this is version number 1. You can use that as an external ID. So usually internal ID defined by the system, usually to keep track, defined by the users for a specific purpose. Another consideration is the difference between behavior and responses. You can have systems, machine vision systems that respond in a synchronous way, or systems that respond in an asynchronous way. If your system that responds in a synchronous way, you can use, for example, a call prepare recipe, and when you call this method, you will assume that the recipe will be prepared as soon as the method returns. That means that when the version finishes, it's ready. But if you can also have an asynchronous system in which you can call or prepare a method, and then the method returns automatically and tells you, I'm going to finish this in a particular time. And then in the background, it prepares the recipe, and when the recipe is finished, you can then trigger an event that says recipes prepare now. And then you can use it. In the meantime, you can then continue to call other methods, for example, preparing other recipes, and the system will continue to work. Lastly, as I mentioned, we have implemented all of this in Merlik, and this is a simplified view of our Merlik architecture. We have the Merlik runtime, which contains the state machine, the recipe management, the configuration management, and as I mentioned, some part of implementation of configuration. This is the part that controls the cameras, that has the configuration and the recipes. And additionally, we have what is called the Merlik communicator, which you can have multiple plugins that allow you to communicate between different vision systems. One of these plugins is obviously the OPC UA for Machine Vision Server. And because of the concepts of the OPC UA are so generic, we decided to implement it not only in OPC UA, but also as an API, where we can use that API to create new plugins that use the same core concepts. In this case, for example, our MQTT plugin has also a recipe prepare trigger, has recipe prepare events, delivers results in the same way, and you can use this API to create any plugin that you so desire. So if you have a system that you want to, for example, create a Modbus plugin, an Ethernet plugin for your system, you can do so. Thank you very much. That's all.
Do you have questions?
Any questions?
Any questions? Any at all? Then I will give you more information. You cannot escape me. So this was all that you saw on the screen was all released in 2019. But we have not been sitting idle since 2019. Now we have another part. The release candidate is out. If you reach me, you can get access to the release candidate if you have some feedback on part 2 of the specification. We would like to have some feedback. So if you can reach me, it would be great. Some more information on what part 2 is handling. So you saw that part 1 was only talking about the functionality of a machine vision system or how it works or what you need for a machine vision system to work. With part 2, we have the composition of a machine vision system. What is a machine vision system built of? So what are the components inside a machine vision system? Maybe you have 5 image sensors, maybe you have 10 frame grabbers, maybe power units, display units. All possible components of a machine vision system can be modeled with part 2, and that is what we have. Focusing on use cases of system maintenance, component maintenance, system health, component health, and system and component identification. So these are the use cases that we talk about in the part 2 of our specification. Again, this is a release candidate. Hopefully in first quarter of next year, we'll get a release, and that would be about it. If you need more information, please visit us on the Global Vision Standards, International Vision Standards booth, also in Hall 8, where you not only get information about OPC UA for machine vision, but also for all of the standards that my experts talk to you about. That would be it from our side. Thank you so much.